Hey there, welcome back. Right now, as you're watching this, your brain is doing something absolutely remarkable. It's processing these words, managing your breathing, keeping you balanced, and running thousands of background processes, all while consuming less power than a dim light bulb. About 20 watts to be precise. Meanwhile, the AI systems we're building, they need 1 billion watts to do far less. And as AI adoption explodes, we're heading toward an energy crisis that could derail the entire revolution. But here's the thing, nature already solved this problem. Your brain is the proof. And after 40 years of research, scientists have finally figured out how to build computer chips that work more like brains. These neuromorphic chips aren't just incrementally better. They're showing energy savings of 25 to 500 times for real AI tasks. So today, we're diving deep into why AI has an energy problem, how your brain solved it billions of years ago, and how the chips inspired by biology could save artificial intelligence. Let's get into it. Let's start with the uncomfortable truth. AI is consuming electricity at an absolutely unsustainable rate. In 2024, global data centers consumed roughly 415 terawatt hours of electricity. That's the equivalent of the entire power consumption of France. But here's where it gets scary. By 2030, that number is projected to more than double, and AI is the primary driver. To put this in perspective, a simple Google search uses about 1,000 joules of energy. But an AI query, that can consume over 10,000 joules. You are using 10 to 30 times more power every time you ask for a recipe or a summary. And training GPT-3 just once consumed 1,287 megawatt hours. That's enough electricity to power 130 average US homes for a full year. Now scale that up. Billions of users, millions of queries per second. Think of it like this. If your brain were a car getting 10,000 miles per gallon, current AI systems would get about 0.001 miles per gallon. We're building gas-guzzling supercomputers in a world that needs efficiency. This isn't sustainable, and the tech industry knows it. So how does your brain do so much with so little energy? It turns out your brain doesn't work anything like a computer. It uses 3 specific tricks to cheat the energy bill. First, spikes, not streams. Traditional computers process data like a fire hose, a constant, heavy stream of numbers, even if nothing is happening. Your brain? It uses spikes, tiny, quick pulses of electricity. And crucially, neurons only spike when something changes. If you stare at a white wall, your visual neurons stop firing. They stop burning energy. It's event-driven computing. Second, memory and processing are the same thing. In a computer, memory lives in one building, RAM, and the processor lives in another, CPU. They have to ship data back and forth constantly. In your brain, the neuron is the memory. The data doesn't travel. It stays right where the work happens. Third, massive parallelism. A computer is like one genius doing math at the speed of light. Your brain is like 1 billion people whispering to each other at the same time. Individually slow, but collectively unbeatable. So if the brain is so efficient, why don't we just build computers that way? Because for 70 years, we've been stuck with the von Neumann architecture. It's a brilliant design for calculators, but a terrible design for AI. The biggest problem is the memory wall. Because the processor and memory are separate, a modern computer spends up to 90% of its energy just moving data back and forth. It's like commuting 4 hours to work for a 1-hour shift. You burn all your gas on the commute, not the job. Then there's the clock tyranny. Computers run on a global clock. Tick, tock, tick, tock. Every transistor has to march in step billions of times a second, whether they have work to do or not. It's wasteful. And finally, precision. Computers calculate everything to 15 decimal places. Your brain? It operates on good enough. And for recognizing a face or driving a car, good enough saves a lot of power. So what if we broke the rules? What if we built computers that had no clock, no separate memory, and only used power when data actually moved? That is neuromorphic computing. The word comes from neuro, nerve, and morphic, form. These chips implement the brain's rules in silicon. 1. They utilize spiking neural networks. They process information as events, not numbers. No data, no power usage. 2. They use in-memory computing. The memory units are the computing units. The commute is canceled. 3. They are asynchronous. There is no master clock. Parts of the chip can be fast asleep while others are working hard. This sounds great in theory, but for decades it was just science fiction. Until 2025. Here's the part that people are missing. These chips aren't just lab experiments anymore. Real hardware is hitting the market, and the numbers are staggering. In March 2025, researchers proved they could run a large language model on Intel's Loihi 2. The result? It consumed 50% less energy than a traditional mobile GPU while processing text faster. That is a massive leap for a first attempt. Then there's IBM's NorthPole. Published in the journal Science, this chip obliterated the competition in image recognition. It demonstrated 25 times better energy efficiency than current GPUs. Imagine cutting your AI electricity bill by 96%. But the real shocker is a smaller player, Innatera. In May 2025, they launched the Pulsar chip for sensors. They're not claiming 50% savings, they're claiming 500 times less energy consumption. That means a battery-powered sensor that used to last a week could now last 10 years. So where will you see this first? Not in ChatGPT, not yet. You'll see it at the edge. Neuromorphic chips are perfect for things that run on batteries and need to make split-second decisions. Robotics and drones. A drone could now use a spiking neural network to dodge trees in real time without needing a heavy computer or an internet connection. Smart cars? Companies like Mercedes have explored neuromorphic tech for voice and sensor processing. Why? Because you don't want your car's safety systems to lag because of a bad cell signal. And industrial IoT, factory sensors that listen for the vibration of a braking machine, running for years on a coin cell battery. It's not about replacing the massive data centers yet, it's about putting intelligence into everything else. So here's the bottom line. The race for AI in the last decade was about scale, bigger models, more data, more power. The race for the next decade is about efficiency. Neuromorphic computing proves that we don't need a nuclear power plant to run a brain. If we can shift just 20% of AI workloads to these biological chips, we could save enough electricity to power millions of homes. The answer to AI's biggest problem wasn't in a bigger data center. It was inside your head the whole time. If you found this helpful, subscribe to the channel for more deep dives into the technology that's actually changing the world. Thanks for watching, and I'll see you in the next one.